off. That's why you can't hear it. I'll be out. I'll survive. Okay, some things. All right, so today we're going to start plate tectonics, which is really exciting because it's some of the, I think, most exciting, most interesting basic processes in Earth that I enjoy thinking about, and it's part of my research. And I think, well, a lot of you too identified plate tectonics as being something that you really wanted to learn about in this class. So it's how it's turning out is that there's quite a few slides, so we're not going to get done today. What I'd like to do is to make sure that we have time to talk about the labs. There's a pre-lab that's important for this week that I'll explain in a minute, that I want you to start before Thursday. And then Thursday, hopefully we can pick up on the main part of the lab. And the pre-lab is really basically just downloading Google Earth and not using the website. So there are two ways that you can use Google Earth. One is through a web browser, and one is by downloading an app to your computer. I need you to download the app to your computer for this one. And you're going to be downloading some other files from iLearn too. So for the pre-lab, let me show you I'll share the screen with you in just a sec. Okay. Let me open it and find the right thing. Okay. Here we go. Okay, so there's iLearn. Okay, so let me just collapse these. And collapse that and that for now. Okay, so Lab 5, Exploring Plate Tectonics. All right, so I put these instructions here. So this is these are the worksheets, as it says. So download the set of worksheets that you'll use. Then you need to download Google Earth. So this is a link to the right Google Earth Google page for Google Earth. And I think if you click on this one, it takes you directly to the thing you've got to click to make it even clearer. So if you haven't done that yet, please, after this class, do that, or even like start right now while we're talking about it. But download that app, get it installed. I think you'll end up downloading like a DMG file or something like that. You got to double click on that and it installs, just like any other app. And then you need to come back and also download this one, which is a geologic map of California that you'll use in Google Earth. So the file type is a KMZ file. The second one is a KML file. Both those types of files are files that you open in Google Earth. So I want you to open the geologic map of California, and I want you to open this one, which is topography. And I think it's for the entire contiguous 48 states. I'm not remembering exactly right now. I know for sure it's California. I'm going to add that the pre-lab simply asks you to navigate through Google Earth so that you kind of get used to using its buttons and like know where to find things, know where to like look for your layers, like the geologic map of California, the topography, because you don't always want to look at those. Sometimes you just want to see Google Earth, find your place, and then turn those layers on so that you can see what you're doing, because it kind of obscures the city names and the roads and all the stuff that you're used to looking at on a normal Google map. So that is, it's short. It should be easy. I think the hardest thing is just getting it installed on your computer correctly. So please try that before Thursday. Hopefully you can finish before Thursday. And then this is the main lab. 5B is the main lab. And this is the one that we're going to use. There's 7 other files, small files, that you'll also download to use with Google Earth. So you need to get the worksheets that are for the second part and download these 7 files that I've tried to make clear here, which ones. So you're going to grab a map of the tectonic plate boundaries. You're going to grab 3 files for different size earthquakes. So for the very small earthquakes, magnitude 1.0 and up. But I think it only goes from magnitude 1.0 to 2.5. And then there's 2.5 to 5.4, and then 5.4 magnitude and higher. So these are the really large earthquakes. The questions really kind of ask you to distinguish between the large and small earthquakes and also their depth. And you'll see a legend on those that will explain what the color coding is for the depth of the earthquake. Then you're going to grab this file, which is for active volcanoes around Earth. Then I also ask you to grab this file that shows specifically the Hawaii Emperor Seamount chain of islands. So there's a question that asks you about that, because actually hotspots can be used to track the plate motions through time. If you can date a basaltic lava that comes out of Hawaii, then you can go back to all of these, the older islands that are no longer active. You can go back to the seamounts, collect samples and calculate an age for those. And then you can like look at that, measure the distance. If you know how old they are and you can measure the distance from the current hotspot location to that spot where you collected the sample, then you can calculate a plate motion rate. And it also just, you can see directions as well. So these are really cool. I'm getting all excited. I think you're going to have a lot of fun with this. And then the age of the seafloor. So I think you've seen maps like this before in the lecture. I think so. If not, you'll see it today. But the coolest thing about these and about using them in Google Earth is that instead of looking at a 2D map, it's on a globe, right? So you can spin it and you can see exactly where all this stuff is happening. And I think it makes it more dynamic and more interesting. And not only that, but you can layer all these. So you can only show the volcanoes, or you can show volcanoes and earthquakes and the age of the seafloor, and you get a lot of information together. Anyway, that's what you're getting yourselves into for the main lab. And this one, like, you know, it's a little bit more involved than, it's probably more like the TopoMap lab in terms of how many questions, all those different things you're supposed to do. But next week we'll have a relatively short lab, so I hope it kind of makes up for it. I'll try to like balance that out, so they're not always long labs, that sometimes you'll get short labs. Okay, let's see. All right. I have been grading labs, and I did announce in those, I sent out a really long email, sorry about its length. I just want to make sure I'm communicating everything to you. So if you haven't been reading those emails, I suggest that you do read those emails. I've been trying to send out Sunday, they've been coming out Monday sometimes, but Sunday-ish, that explains what's going on. For example, that I graded the TopoMap labs and the first and second labs are done. So you can go in and see your scores. Every lab so far, there have been one or more people who do really well, who are following step-by-step instructions, reading the supplemental material, like clicking those links to go to those extra web pages, reading that to explain some things, and then completing the lab. It seems pretty clear to me. I mean, I don't know exactly, but I'm gonna take an educated guess that the people who did less well, and for the TopoMap lab, I mean less than the high 70s. If your score was less than a high 70s number, I think probably what happened is you didn't go to those extra websites and read through those, and you were trying to do this too quickly. But that's all right, right? Because you're gonna drop the lowest 2 scores, and you've got 15 labs, 1 every week for this class. So, or is it 16? Might be 16 because we got that extra topo map lab in. But so there are a lot of labs, and if you continue to do better each time, then those aren't even going to be a blip on your radar, right? Those will cancel out, and then your lower scores will be nothing compared to the other 10 or something. Now, notice that I sent out one of those emails, and I said something very important. Remember, I said I would drop the lowest 2 labs scores. I would drop the lowest 2 quiz scores. And I said I would drop your lowest of the 3 exam scores. That includes the one that you'll take during finals week, which is only the last like third of the class. But I'm only going to drop the one of the exams if you get me 10 out of those 15 or 16 labs, if you get me 10 of those labs on time. So by the deadline. And I think that's pretty fair. I think like 2/3 of the labs, as long as you can get those to me, and I ask for them a week after we're talking about them, right? So this week's lab is the Plate Tectonics Lab that uses Google Earth. You've got 5A, 5B. Those aren't due this Friday, they're due next Friday. So you have plenty of time to work on them. And so you should be able to get me 10 labs on time. And to give you that incentive to get them to me on time, I'm suggesting that I drop one of your exam scores, the lowest exam score, if you can do that. So I hope that that's a carrot and not a stick in terms of like motivation, you know, that like old saying about horses. I don't know if you know that's the old saying, but the horses don't want the stick, they want the carrot. I'm not calling you horses. Haha. Okay. Where are we? Any questions about that policy? Oh, I see someone like, let's see. What about the dating lab? So the dating lab is due this Friday. And I have not started scoring those. I'm in the middle of scoring the fossils lab, and those will be done probably today. I already have the key and the grading rubric done. So I'm working on these. Did you have questions about this lab? Is that what you were asking about? That was Ashanti, I guess. So I'm happy to take, oh, go ahead if you were going to talk. No? Okay. I'm happy. The dating lab is due this Friday, right? Because we talked about that last week, so it's due this week. So if you haven't turned that in yet, you still have the rest of this week to finish it. I hope that you're starting these labs in the week that we talk about the topic, so that the concepts are fresh in your mind, and that you're not waiting until the last minute, because that's not the way to do these, really. It's you're going to get very little out of them. And I realize that for some of you, probably this class is just like, whatever, I just want to like turn it in and get my points and get out of here. I understand. I'm trying to convince you that this is really interesting stuff and that you should want to learn about it. And that's why I'm hoping that you'll follow those extra links in your labs to get the supplemental material is the wrong word. It's more like complementary material. That's complement with an E, not an I, meaning it goes with it, together with the worksheets and whatever main website there might be, that there are other bits that go with those labs. So for the fossils labs, that would have been the videos of Lisa White, who showed you the fossils, and she gave you some, like, she gave you some, what's the word? The word for words, not terms. That's not the right word I'm thinking of, but she gave you some terminologies. For instance, the word valve. I don't think you saw that anywhere else in your lab. So if you wrote the word valve in your lab, that tells me that you watched Lisa's videos, because she talked about the two halves of clams, like each half being a valve, one of the valves. So you should have watched all of the different, she talked about each of the different units in your lab one by one and pulled out those fossils. And then there was the virtual field trip, which didn't have a lot of writing to it, honestly. There wasn't a lot to read. The most important thing out of that was to go and magnify, to like click on the images, and so that they would magnify for you and you could see what was in the pictures better. There was also one like panorama of the outcrop that you could zoom in and see the fossils in the sandstone, in the rock. It's not soil. None of what you looked at was soil. That was all rock. And it might have been crumbly rock, but it was rock nonetheless. It just means it was less well cemented together, those sand grains. So there were, those were really important parts of that lab. If you haven't, let's see, the fossils lab. So I think that the geologic time lab, that only required that you understand the different laws for stratigraphy, the law of original horizontality, the law of superposition, cross-cutting relationships. And I put those at the beginning of your lab. I also explained them in lecture. If the description wasn't enough, then going to the lecture and looking at the examples we looked at during the lecture and listening to me talk about how they work and how you guys answered the questions, that's the way to do that. If you haven't finished that, I recommend, and you're stuck, then I would recommend that. The last question was tripping people up on the relative age dating. It was asking you to put time brackets. And in case you weren't here, I did talk about this on Thursday, but for the time brackets, you were given paleo on the side of the cross section. It was labeled Paleozoic and Cenozoic on the side. And then you had rocks that were down at the bottom of the Paleozoic and they like kept going up. And then you had 3 units in the Cenozoic. So you had some notion of the age of those units. And what I suggested you do was to refer to them. You know, if you were talking about the rocks, you would say the lower, the middle, the upper part of the Paleozoic. But because you're talking about time in that question, you would say the early part of the Paleozoic, the middle part of the Paleozoic, and the late part of the Paleozoic. So the words that you use change depending on whether you're talking about the rock in the outcrop or whether you're talking about the age, the timing of it all. Questions about that, since that hasn't been, the due date hasn't passed for that one yet? So to answer your question, yes, you guys, some of you are still working on that. Some of you have turned it in. If there are no more questions though, I think I'm going to continue on to the lecture material today and start talking about plate tectonics. So hit me with a question in the chat or go ahead and unmute yourself and ask me any questions you've got. Okay. I'm going to go find the lecture then. I started off, it took me so many days to put this lecture to, oh, that was another thing I wanted to say about the labs. So a couple of you have said things to me that make me think like, maybe you think these labs are harder than they should be because we're not like sitting together face to face. That's true. They would be easier if we were face to face and we could sit together in a 3-hour lab and I could look over your shoulder and you could show me your work and all of that. I mean, some of that's possible, and we can share screens like on Fridays or on Thursdays. We could take time to do that. But you know, that part of it's not possible. But I designed each of these labs from scratch or borrowed them from someone who designed them for use online. So these are all intended to be used in online classes. That means that you're getting step-by-step instructions on how to download this, or you know, how to download a topographic map, for example, those sorts of things that otherwise might not be there. Just so you know that yes, these labs were designed for you, for this class, and for online learning. In fact, you know, all of your instructors spent the entire summer unpaid and working on getting classes ready for this year. And it was a lot of work, trust me. And even that, even then, I didn't have a final plate tectonics. Like I had a couple of different lectures like ready to roll, but I updated everything and let me stop sharing this. I updated everything and I put in the latest material that I could find with the best graphics, all that kind of stuff. So I really have thought about your experience in this class, and I am trying to make it better for you as good as I can. Okay. All right, so let's start here. And make this as big as I can. Okay. Media. Okay. So the things that we're covering in this lecture, and I'm putting these lists here because, like I said last week, they're a little bit different than what's covered in the textbook. That list of items is on the next slide, what's included in the text. But just so you know what's included here, that you can go back and see what I talk about. If you miss lecture, for example, then you'll know. Also, I am putting the audio transcript, now that I'm recording to the cloud, I'm putting the audio transcript also on iLearn, either in the lecture, wherever I put the slides, so wherever I put the recording of what I talked about. So if I'm talking about mostly this plate tectonics lecture set of slides, I'll put it in the lecture folder. If I talk about one of the labs too, I'll label it that I talked about the labs, but you're not going to find it also in the lab section. So you need to like look at the current content in both of those folders to find what it is you're after, should you miss class. Anyway, so there are some things in this you probably haven't heard of isostasy before, maybe in physics. Earth science is one of those sciences that it's a physical science, and it's got its own set of rules, right? But it calls on chemistry, it calls on physics, biology. You learn that looking at the fossils lab. So we're using all the other sciences, even like astronomy, because we do planetary geology. Like earth science touches a little bit of every kind of science. These are the concepts from your textbook. Specifically, the text talks more about the background, like leading up to, like, how did we get to this idea of plate tectonics? Because it wasn't until the very earliest stages of the idea that the continents were moving. I mean, it goes back a ways. As soon as we started to have global maps and we could see that the continents looked like they kind of fit together, and after people started describing fossil assemblages that matched in Africa and South America, those sorts of things, the ideas really didn't develop. It really wasn't until we started mapping the ocean floor between the two world wars, and then in World War II in particular, that data was gathered, and that was the first time that anybody saw a ridge. People thought the ocean floor was flat, a flat, muddy bottom. They didn't know there was topography on the seafloor. There are ridges. There are, like I'm talking about all this stuff. There's a lot to see. So those were, and I'll highlight who did that, who did the first map. But until that happened, and until they dragged magnetometers across at the back of the boat, across the seafloor, and saw this set of parallel signatures, magnetic signatures, it would be like if you were 100 kilometers away from the ridge in this direction or 100 kilometers away from the ridge in that direction, you got the same signal from the magnetometer. And then people started to put this together, and the idea that, oh, there's new crust being created at those ridges, and it's spreading apart. The plates are moving apart there. That we got to the idea of plate tectonics. And so it really wasn't plate tectonics until the mid to late 60s. It might sound like forever ago to you guys, but it's not that long ago. It really isn't. Compared to chemistry and physics, even biology, geology is a young science. All right, enough tangents. I put this in here because I wanted you to see these arrows. Each of these arrows indicates, the red arrows indicate an absolute plate motion, and the size of the arrow indicates how fast it's moving.
Excuse me,
Yeah,
Professor?
sure.
Are you sharing screen? Because it's still.
Oh my God, I did it again. Thank you. Yeah, you guys, I thought I was. Actually, I did click on it. How weird. Okay, I did click on it that time. I don't know what happened. I blame Zoom on that one. Okay, can you see those now?
Oh, we're still seeing like the whole like.
You're seeing all of them, right?
Yeah.
Okay, good. I just wanted to make sure you could see them. Still, you can see them, right?
Yeah.
Okay, cool. Sharing is paused. Why is it? All right, so I'm gonna go forward. So this is the list I was talking about. This is what I was starting to talk about, was the arrows. You can see this one, right? With the plates.
The list.
No, you can see the map right now.
No, it's still the whole gallery, but it's like.
Really? Okay.
Yeah.
I don't know what's going on here. Oh, brother. Okay, wait. Oh, you know, it still thinks, oh my God, I don't know what's happening here. All right, let me stop all the sharing and try over. Zoom is definitely not perfect. Okay. I don't think I'm sharing. Okay. Okay. Can you see the maps this time?
It's still the gallery of all the slides.
Are you kidding me? What is happening? Okay. I don't know what's going on. I wonder if it's because I have some movies in this lecture, Let's see if I can just make these really big slides then. Let's do this. How's that? Still the slide gallery or the map?
It's still the slide gallery, but it's zoomed in.
Oh, brother. I'm so sorry about this. I don't know what's going on. So you guys can see that map well enough? You can read the text and all that?
Kind of.
Oh, okay. Wait. Let me, oh, boy.
Which map are you referring to?
Well, it's either, so it's a map with arrows on it. It's this one, this third slide that I'm trying to show you. But any of them, I'll take any of them at this point because it's like, can I zoom in more? Let's try 400. No, it doesn't, it only wants 200. Oops. 200. Oh no, what is happening? Okay. Let me try this way. Okay, I'm back in the slideshow and you should be looking at a map of the world with arrows on it.
The screen is not shared.
Oh no. What is going on? Like, I don't even see, when I share, there's like there's a green outline on the screen that I'm sharing and it's not showing. It like disappears. I really don't understand what's happening. Let's try one more time. Come on. Okay. A map with arrows, a map of the world with arrows on it. Still nothing? If it's still nothing, I'm just gonna work from the slides themselves. Okay, because I'm not hearing anything, I'm just gonna assume that you can't see. I'm gonna do it like this then. Can you see this? Can you see this one well enough?
Oh yeah, we
Yeah,
can
we
see
could
that
see
one.
that one.
Is it big enough to read the text and all that?
Yeah.
Yes.
Okay, we're gonna go with this one then. I have no idea what that was all about, but you bet I'm gonna contact Zoom after class. Okay, let's try again. Okay, so plate tectonics. So the plates are moving in these directions. The arrows point at that point on that plate. It's pointing in the direction of motion that we're getting from like satellite data. So these are accurate measurements, and the length of the arrow indicates how fast. So the length of this arrow indicates 5.5 centimeters per year. So if the arrow's longer, this is probably like 10 or 12 centimeters per year. Do you guys know your metric system at all? 5 centimeters is probably this much, maybe, I don't know, maybe like the width of my hand, maybe a little bit bigger than my palm. My hands are kind of small though. 10 centimeters is maybe like this. So maybe like two hands kind of together. It's definitely not, it's much less than a foot. A foot's like this. 10 centimeters is like this. So that's, I mean, the plate is moving pretty fast. Like, we can't watch it move, but we can certainly measure it and measure it really accurately because it's moving fast enough. So do you know any other things that grow, that move this fast? I almost gave it away. Your hair and your fingernails grow as fast as as the plates move, basically. Those are great analogies. So you can't really watch your fingernails grow, right? You'd have to have a whole lot of nothing else going on to do that, but you probably couldn't even see it happen. So you're not seeing the plates move, but over time, we know they move. Part of how we know they're moving is we get eruptions of volcanic material. at the mid-ocean ridges and at subduction zones, and we get earthquakes. You know, has everybody in class, like who's felt an earthquake before? Can you give me like a thumbs up or something in the participants?
Many, many times.
Oh yeah. Tell me about it, Kay. I think that was Kay.
Yeah.
Where'd you feel?
I remember it was maybe like 7, 8 years ago, I think. I remember, yeah. I live in Concord, so in the East Bay.
Uh-huh.
And at the time I was living in Pleasant Hill with my parents, but there was an earthquake. I think it was around like a 5 maybe, but I remember it was one of the biggest earthquakes I'd ever felt. And in my house, all of the cabinets opened up and stuff was like falling on the floor. And
oh wow.
like,
So you were kind of close to the epicenter.
Yeah. No, I actually was. The epicenter was rather close to my house, but
The Hayward Fault or the
cabinets and all the cabinets in my bathroom opened up and everything fell out. And I was in the bathroom when that was happening. And so all of the stuff was like falling down at my feet. And I was trying to stand underneath the door jamb and hold on to it. And it wasn't fun. I've felt smaller ones, but that was the biggest one I've ever felt. I think it might have been around a 5.0.
Yeah. A 5 will definitely catch your attention. So I see like 6 or 7 hands went up. So, you know, it's not everybody. You know, hopefully, I'll wish for a small earthquake so that you can all feel one. I won't wish for a big one. And plus the small ones release some of the stress that's on the plate boundaries. And so having a lot of smaller earthquakes will prevent us from having bigger earthquakes.
I just felt a small one recently.
Oh, where?
I was actually just in my house and I was just doing a bit of homework and I just felt like a little shakiness.
But where is your house?
I live like in California.
In Southern California? Sorry, I didn't hear your answer. Yeah, if you lived anywhere in California, there's a good chance that you felt one before. And if you haven't felt one yet, you will at some point in your lifetime. We're going to talk about earthquakes and seismology next week. And there's a lot of cool stuff there too. So you're going to enjoy that one too. But I just wanted you to see, like, look at North America is moving to the west. The Pacific plate is moving to the west, northwest, faster than we're moving to the west, the North American plate. Actually, I'm sitting on the Pacific plate right now. You guys might be on the North American plate, but I'm on the Pacific plate. Yeah, so that actually works out to help the San Andreas Fault. I mean, that explains its horizontal lateral motion sort of moving to the north there. We'll talk about that more then. Let's talk more about the plates first. I just wanted you to see how fast they move, because it is fast. Now, I was talking a minute ago about the mid-ocean ridges, right? These are important because this is where all the new crust is forming. And the earth isn't growing in size. So that means we have to destroy crust somewhere else. And we destroy crust. You've heard of the Ring of Fire? The Ring of Fire is around the Pacific. Everywhere you see these arcs, we're gonna get a close look at them this week. These are subduction zones all through Central America, South America. They're all subduction zones, and there are more over here too. The Mediterranean, there's a subduction zone to the north under Europe. The subduction zones are where that crust is destroyed and pushed down back into the mantle, kind of mixed up a little bit, and then we see evidence that crust comes back. in places. I've seen, for instance, my PhD was on this mountain range here. It's kind of hard to see. It's in the, right, it divides Europe from Asia. This is called the Ural Mountains. And my PhD area was in the south. And I collected graphite. It was, my rocks had a lot of carbon, like organic carbon in them. And it shows up as graphite, which is just carbon. Graphite's the stuff that's in your pencils, right? It's not actually lead, it's graphite carbon. And when I measured, and these rocks were involved in subduction of the European plate beneath Siberia. And the graphite had an organic carbon 1312 ratio to it, and a signature, that number that I got is what you get out of plants and animals on the surface of the earth. And these rocks had been subducted down into the mantle and came back. So it was, I mean, we see subducted material pop back up in subduction zones sometimes, slices, not all of it. Most of it gets recycled, but some slices of crust come back and we can measure it. We also see the signatures of mixing in the mantle in the lavas that come up at mid-ocean ridges or in other places like hotspot volcanoes. Anyway, all of this topography on land and all of the bathymetry underwater can be explained by plate tectonics and erosion. You can't forget about the erosion part. Okay, so, oh yeah, the point I wanted to make here is that the continents are clearly sitting up higher than the ocean floor, right? I mean, it has to be, otherwise the continents would be flooded and they'd be part of what's underwater too. But they're not. And the reason that they're not is isostasy. That's the next slide. The continents are made out of different material than the seafloor, than the oceanic crust. Continental crust is you can average it all to be kind of like a granite. So if you haven't seen a granite, I'll show you some today. It's light colored. It doesn't have a lot of dark minerals in it. The dark minerals are dense. They have the iron and magnesium. So if you've been to Hawaii and seen the black basalts there, or maybe been to some volcano in the Caribbean or in Central America, maybe, you've seen basalts that are blackish or dark gray. Those are really iron and magnesium rich, and they're dense and heavy. And because they're dense, they kind of sit lower on the asthenosphere that's propping up all of the plates. And the continents are less dense, so they sit up higher. And they have also, if you've got a high mountain, you're going to have a corresponding deep root to kind of compensate isostatically. That's what this is all about. So look at this slide first, the bottom left, where these are blocks of different densities. Imagine these blocks here are like the continents. And do you see how thick it is? There's this thick root that goes deep down into the earth, kind of like an iceberg. Icebergs, most of the iceberg is hidden underwater. And that's because it's floating there, it's balanced. Just like, imagine if the water was the asthenosphere over here on the bottom right. And that up here, these are the continents. If you put a load onto that gooey, plasticky asthenosphere, it's gonna push out of the way and kind of make room for the continental root that's there. And the denser oceanic crust, it's thinner, and it doesn't need that nice deep root to balance itself out in the asthenosphere. And so it looks more like this. It looks more like the edges of that iceberg. But let's stop talking about icebergs and look at the actual Earth. Here's the continent, and here's a mountain range. You can imagine, let's just imagine this is the Sierra Nevada, so our local mountains, and this is the Pacific Ocean out here. There's a thin, maybe 3 to 4 kilometer to 7 to 8 kilometer thick crust. It's not very thick at all, and it's a lot denser. This P is actually supposed to be the Greek symbol rho, which looks kind of like a P. And the that is the abbreviation for density. The density is 2.9 compared to 2.8 or even less in the continents. The mantle is 3.3. It's much denser. But so that it's the dense mantle is kind of propping the crust up, and the asthenosphere is leaving room for these deep continental roots. So the Himalayas, for example, I'm going to show you the next slide. I'll show you the Himalayas are like 70 to 80 kilometers thick for this reason, for the isostatic balance, or isostatic compensation is what you would call it. And you can actually calculate, and I did this in my undergraduate tectonics class, where you calculate the densities and the thicknesses of the mantle and of the crust. And sure enough, it all mathematically, it's math and physics, works out to explain this really well. So it's really all about density. Next slide. So this is a map of crustal thicknesses. Here's the Himalaya right there, and it says 70 in those rings. So everywhere it's kind of brownish, orangish color, the crust is thicker. So even Antarctica has some 40 kilometer thick crust. The Andes should be similar to the Himalaya, actually. I would say that those might be as deep. 70, probably 70, maybe not 80 kilometers thick, but they rival the Himalayas in terms of that mountain range. We've got some thick crust out here. The Sierra Nevada is fairly thick, but everywhere that it's green is it's the older parts of the continents, the inactive parts, meaning there's not a lot of plate activity going on there. And so those are kind of like 30 kilometers, 35, 40 kilometers thick. They're a bit thinner. And then the oceans, you see, they're all mapped. These are lines, just like topographic lines. These are isoplests of different thicknesses. So that means the Pacific Ocean crust is less than 10 kilometers. The Atlantic crust is less than 10 kilometers. Same with the Indian Ocean, the Arctic Ocean. So they're all thin. Does that make sense to everybody? The isostasy? Because I would like to hear questions. It's not a simple topic. And, oh, someone's got wait, let me clear these. I don't know if you had a new question or not. You can put your hand up if you've got a question in the participants window. I can't see the chat at the same time though. If somebody could monitor the chat for me and let me know if there's a new question, like by unmuting yourself, that would be fantastic. But if you've got a question about isostasy, please ask. I'm gonna move on though, but stop me if I should wait. So I want to give you some vocabulary. That's the word I was looking for earlier for when Lisa was talking about valves and all that. Okay, so Felsic and Mafic. I want you to learn these two words. These are generic, they describe a generic composition. They describe the continental crust is overall it's felsic, which means it's got feldspar, which if you'll have some in your rock and mineral kits, in your mineral kit specifically, and silica. So fel and silica is where felsic comes from. So it means high silica, like maybe 65, 70, 75+% silica. These are light colored rocks. They're not very dense. And they tend to have more of the sodium, potassium, and aluminum compared to the mafic rocks. The mafic rocks, so this is like the continents, right? The felsic rocks are like the continents. The mafic rocks are like the oceanic crust. So actually I should write, this is similar. How do you do one of those squiggly lines? That's not the one. I'll just say equals about granite. And mafic rocks are approximately like basalt. If that helps you to remember them. A granitic type composition is a felsic composition. A basaltic composition is a mafic composition. So they're a little bit interchangeable, but the felsic and mafic refer to the chemistry, the actual composition, the elemental composition, and basalt is a specific rock type, and granite is a specific rock type, just so you know. But the mafic rocks, the basalts, are high in magnesium and iron. That's what mafic comes from, the ma and the th, because the symbol for iron is Fe on the periodic table of elements. So that's where that comes from. And they're low in silica, more like 55% or less, maybe 45 to 55% silica. They're dark and they're dense. And anytime different composition rocks are involved, that's going to affect the geodynamics, or like how the rocks are moving around, like how dense they are affects whether they get subducted or maybe pop back up, that kind of thing. There are lots of ways that they impact our understanding of plate tectonics. So learning about rocks is also learning about plate tectonics. These are some examples of rhyolite. These are from near Lassen or Shasta. I think it's actually closer to Shasta area, but it doesn't matter. The idea is that these are felsic. So it was an actual ash deposit, but it's rhyolitic. That's the volcanic name that's the equivalent of a granite. So these are felsic. And here's a basaltic lava flow. It's not lava anymore, right? It's basalt, but it was a lava flow. And do you see how dark it looks in comparison to the rhyolite? That's the kind of difference I'm talking about. So these dark, dense rocks compared to the light colored rocks. So I hope that I can use the words felsic and mafic going forward, and that will make sense. Here's a little bit more about felsic and mafic and all of that. These are the general terms, felsic, mafic, terms that we use to describe different rock types. Here's a granite. So if you haven't seen a granite before, this is what they look like close up. They're light colored from the feldspars and the quartz. This is quartz, that's feldspar. This is the pink stuff is another feldspar. And they've got like specks of black material. So those might be some biotite micas. So there's a little bit of iron and magnesium in those rocks, but it's a small percentage. It's maybe 5%, definitely less than 10% of the rock. The basalt is down here. So it's a dark, dense magnesium and iron rich rock. How you read this plot is these are the volcanic rocks that are the chemical compositional equivalents to these plutonic rocks. So these rocks these are all igneous, and igneous rocks come in two varieties. You're either, and an igneous rock means the IGN part of that word comes from the word fire, and in Latin, I believe. It's either Latin or Greek these words come from. I think it was Latin. It means fire. So think of these as originally all of these rocks were molten. They were a molten magma. We call them magmas when molten rock is underneath the surface. You don't call it lava until it has actually erupted onto the surface as a molten rock. So these were all magmas underground. The Plutonic rocks, they're also called intrusive. Sorry about all the vocabulary, but I'll try to stick to Plutonic. The Plutonic rocks all crystallized underground. And so they cooled slower, much slower. And that's why the crystals are large enough that you can see them with your naked eye. You don't need a microscope. So this kind of looks, I mean, it's all one color, but you can see the individual grains. It almost looks like a sand, but it's not. It's there. These are olivines, or there's a common name, peridot, which probably comes from peridotite. But the peridot is the gem name of olivine. So these are all the plutonic versions of these volcanic rocks. All of these are volcanic or extrusive. They were extruded onto the surface of the earth. And so there's rhyolite as an equivalent of the granite. This is a gabbro. That's the plutonic equivalent of the basalts that I've been talking about. But I tend to go back to the basalt and to the granite as my two examples of felsic and mafic rocks. We just use the word intermediate composition if it's somewhere between felsic and mafic. So an andesite named for the Andes Mountains, or a diorite, depending on where these rocks cooled, is what we would give the rock name to an intermediate composition rock. And then ultramafic, which means it's even less silica and more iron and magnesium in these. And you don't find these, this is mostly the mantle. And we only find ultramafic rocks on the surface of the earth where mantle rocks have made their way to the surface. So sometimes in subduction zones, rocks get pushed up onto the edge of the continent. That's what I'm talking about. Okay, and this plot here is simply a graph showing how much silica, how silica varies. So the SiO2, from 70 down to about 40% they have for ultramafic. That's how it varies. If you remember 50 for the mafic and 70 for the granite, that'll be great. The mineral composition. So this is supposed to be a plot of the dark minerals in this darkish green, and the white color is supposed to be the light colored minerals like feldspar, iron quartz. And these are the relative proportions of how many dark minerals are in the felsic rock. So let's say less than 25% in the felsic rocks are dark minerals. And in the mafic rocks, it's maybe half of the rock is dark minerals. This looks a lot more like, it looks like there's more than half of the minerals are dark in here, but that's because there's a lot of feldspar in there. You can't see with your naked eye. You kind of need a microscope to see all that. And I would let you see that if we were in class. I can come up with some microscope images for you when we talk about rocks and minerals. I'll definitely show you what they look like under the microscope. Okay, so stop me with questions, or you can put your hand up in the, you can raise your hand in the participants window if you want to stop me. I will see those. If you don't want to interrupt me, that is. Okay, so different kinds of plate boundaries. There are three basic types. A divergent plate boundary. So divergent means they're diverging, they're moving away, the two plates are moving away from each other. So this applies to all of the mid-ocean ridges. That's the Mid-Atlantic Ridge, the East Pacific Rise. All of those oceanic plates are separated by, they have a divergent plate boundary somewhere in them. Iceland is one place on Earth's surface where the Mid-Atlantic Ridge is actually exposed. I'm getting there one day. I haven't been to Iceland yet, but I'm gonna go because it's on my bucket list. You can get cheap flights from some of those like cheap airlines in Europe. If you can get yourself to Europe, you can get a cheap flight to Iceland or a stopover on the way. Anyway, that's another point. The Red Sea Rift, the Baikal Rift in Russia, the Red Sea Rift in the Middle East. Those are places where there are divergent plate boundaries, and I'm going to show you examples. There are convergent plate boundaries, like subduction zones. There are different kinds of subduction zones or different types of convergent boundaries, but we'll get to those on Thursday. This is where one plate, where two plates come together, and one plate wins and the other plate doesn't. So one of the plates is going to be pushed underneath the other one. It either pushes down at a steep angle or it gets pushed under at a shallow angle, like in the Himalaya and Tibet, or in the Andes or Japan or the Alaskan or the Cascade Range in Washington. Those are steep, diving, subducting oceanic plates. You get that subduction of oceanic crust where it's an oceanic plate converging with a continental plate. That's where you get those. And that's something I hope you learn in your lab. And then transform plate boundaries. These don't have any vertical motion. These are horizontal for the most part. I lied. First thing I said, I lied. There's a tiny bit of vertical motion on a lot of these faults. They're not perfectly horizontal. For every 10 centimeters, the San Andreas Fault moves, it probably moves up vertically, maybe a millimeter or a few millimeters. So that's actually how we got the coastal mountains here, was because of a tiny bit of vertical motion, but not everywhere. So some examples are the San Andreas Fault. They have the Alpine Fault in New Zealand, the North Anatolian Fault in Turkey, which is really a lot like the San Andreas. You may have heard about some huge earthquake in Turkey. It was going to be on the North Anatolian Fault. And then everywhere that there's a little offset in the mid-ocean ridges, you get small transform faults. So I'll explain all of those, and we'll probably look at that slide again after we had a chance to look at all of them. Okay, so this mostly shows the tectonic plates. There are some small ones, like there's a ton of tiny little plates in the Western Pacific. For sure, it gets really complicated out here. But most of them are big enough. You can see the names, the Pacific plate, the North American plate. Notice there's no plate boundary between the East Coast and the Atlantic Ocean. This is called a passive margin. That means there's no active tectonics going on there because the plate boundary is out here. So the North American plate goes from either the subduction zone here in the Cascades, which starts in Northern California, it goes Oregon, Washington, Southern Canada into that British Columbia. That's all subduction zone. And then we have transform fault here all the way down to Baja. And then behind Baja, there's a spreading ridge that's starting. That's opening up all the way across the US and then out into the middle of the Atlantic. All this whole thing is the North American plate. This is pointing to this little plate here. There's that line. So this whole thing is the North American. The Eastern plate boundary is out in the middle of the ocean. I said that more than once, I know, because I'm trying to point out that just because the continents end where they do, that doesn't mean that's where the plate boundary is, because we've got these passive margins. There's a passive margin on the east coast of South America. There's a passive margin all around Africa, the southern part of Africa. It doesn't get active until you get up into the like the Arabian Peninsula, the Mediterranean. Australia is surrounded by just oceanic crust. The plates are all out in the ocean. So everywhere you see one of these black lines, it's a convergent plate boundary. Everywhere you see a red line, that is a divergent plate boundary. And everywhere you see a yellow line, that is a transform fault. So a transform plate boundary. So what's most abundant? What's the most common plate boundary type of those three? Does anyone want to volunteer for me?
Is it the Pacific one?
The plate boundary type, not the plate, but the plate boundary type. So I'm looking for, is transform plate boundary more common? Is subduction zone or a convergent plate boundary more common? Or is a divergent plate boundary more common? Do you see more black lines, more yellow lines, or more red lines on this map? What do you think?
More black.
Divergent?
Maybe.
It's hard
Yeah.
to say.
There's a lot. What do you think is runner-up? If you think the black is the winner, which do you think is the second runner-up?
Yellow.
Yellow.
Yellow, yeah. What I was trying to get to with that question was like, look how many transform plate boundaries there are that you would never know about, right? Because most of them are on the ocean floor. Because most of them are in these offset parts of the spreading ridges. That's where I was going with that. So actually, if you mapped out, like you measured out all these lengths, they'd be pretty close, I would guess. I'm not sure which one would win, honestly, because there are an awful lot in here of the convergent plate boundaries. But anyway, they're two top contenders. Our continents did not always look like that. The continents, as you might guess, as soon as plate tectonics was active on Earth, we started Earth with, it was just molten. Like we had no continents. We had, maybe there was a cool dead crust. And then eventually we had the segregation of the different layers of the Earth into the core and the mantle and the crust. But we didn't have continents to start with. It wasn't until we started to have eruptions on Earth, have eruptions from the mantle, maybe from the core mantle boundary, maybe from that heat source, that generated the first lavas that might have cooled as basalts. And then over geologic time, we kept growing the crust until we evolved to have these continents. It's hard to go back further than Pangaea, but Pangaea is the name of the giant supercontinent that existed 200 million years ago. So all of our continents were squished together into one giant continent. So you could have walked from South America. Oh, so the map up here shows the country names in the same orientation as this map. So if you can't pick out the continents, like this is South America here, you might be able to pick it out here. And Africa is right here. Here's Africa. Antarctica is down in here. This is Norway. That's Greenland. There's Canada. And Europe and Asia are over here. Okay, so, and there are also lots of smaller land masses that may have been islands at that point. You see, there are a few things that might have been islands. This is our best guess at trying to reconstruct what Pangaea looked like. And there are pieces of evidence that we have that Pangaea existed. And you can kind of like, if you were to like look at this map and you see there's the mid-Atlantic ridge, for example, if you were to put the continents back together, if you were to push them back to that mid-Atlantic ridge where they started, you would see that they would be in this kind of orientation, that they fit right up next to each other. And not only that, but there are mountain belts that they share in common, because when those continents came together for the first time, they created mountains. So there were subduction zones and things going on when Pangaea was formed. And those continuous mountain belts were one piece of evidence that we had. Let's look at a reconstruction. So this is a movie, which may be explaining why the slideshow wasn't working. But this starts 180 million years ago. You pick out your continents first. Here's the US or North America. Here's Europe and Asia, Africa, South America, Antarctica. That's India, and that's Antarctica. That's Australia. Okay, I'm gonna start the movie. We'll watch this a couple times. Okay, they break up. And okay, one thing and so this is the current configuration. I didn't tell you that it counts down the time over on this side as it goes. So it goes, I'll say it out loud, 160, 140, 120, 100, 80, 60, 40, 20 million years ago, and present day. So it goes pretty fast, actually. India doesn't collide with Asia until about around 60 million years ago. And that's what the movie shows. I'm gonna play it one more time. And so you see mountains forming, you see the Himalayas form, and the Alps form, and the Atlantic opens up. The subcontinents, India and Madagascar, push away from Africa, and Antarctica moves to this further south than we did. And we also in this map, oh, it shows the south. We were not in the same positions on the planet Earth as we were either. So a lot of like where we are now, North America, was in the tropics. So we have evidence of tropical animals and plants from that time. Okay, I'm going to go through a little bit of the evidence for Pangaea. Here's North America, Africa, Europe, Greenland, and the brown area. These are called the Caledonian Mountains, or the Caledonides. All of these mountains, so Morocco matches up with pieces of the eastern coast. Norway matches up with Greenland, meaning they originally had collided to form this mountain belt. And it all happened about the same time, which is why we give them the name, the Caledonian Mountains. That means the mountains that were built when Pangaea formed. Okay, this is what it might have looked like. This is South America, this is Africa. This is what the opening of those continents might have looked like. We had subduction going on the west side of South America, and we had this opening up. So this opening is in part compensated by some of this subduction. So we're creating crust here, creating creating an ocean made out of basalt, and it's showing you convection going on in the mantle, and it's showing you melting coming from the asthenosphere here. So there's melting happening and forming the basalts in the crust, and the subduction here is where where we're destroying some of that different crust to compensate. Okay, and you see these stripes that were, these stripes are called fracture zones, and they are like the remnant scars of where those transform fault boundaries were between mid-ocean ridge segments. So there's a little transform there, right there between two segments, and then you have this scar. The reason I'm telling you this is because anytime we get an earthquake on the East Coast, which happens occasionally, the last one I think might have been Washington, D.C. It like freaked people out because they weren't expecting it, like shook the Washington Monument. There's a crack in it after this earthquake. It was because it was a weak point, and it happened on a weak point in the crust that corresponded to one of those fracture zones. So earthquakes still happen even at this time on the scars left over from the opening of Pangaea, which is kind of cool. Okay, here's a reconstruction of some of the the tropical biota I was talking about. And so there were swamps and there are a lot of coal formed in this part of, in Southern Europe, Southern North America, the north part of Africa and South America. That coal, those coal beds are something that has been matched up. There were deserts, you see deserts here and here, salt deposits and coral reefs. So evidence of coral reefs also. So this, all of, so this latitude, look where it is. It's along the equator. That's where these land masses were before the reorganization into the current position. Notice where the South Pole is. The South Pole is actually in South Africa, or close to South Africa, Southern Africa at least. So the south part of India, the southern part of Australia, the south part of South America, they all have striations left over from glaciers retreating. That's another piece of the evidence that we've got. Here's that piece of evidence. So here's Pangaea down here with the South Pole. There's the ice sheet, and it covers a whole different area. The equator is up here. So all these land masses moved to the north over that 200 million years too. And here's the current configuration with those glacial, the pieces of glacial evidence on them. The arrows indicate which way the glaciers retreated. And another, sorry, got away from me. The final piece of evidence I'll give you for the existence of Pangaea are fossil evidence. So there were Glossopteris, I think I'm saying that right. Glossopteris is a plant that can be is found all across these continents, but is found in this zone. Certain animals, like there was this reptile, the Lystrosaurus, I guess is what he was called, found in these areas. A freshwater reptile, a Mesosaurus here. This Triassic is a land reptile that was, this is 9 or 10 feet long. That's a big lizard found across here. So there are these correlations of animals. Now, okay, so, you know, some of them, like this crocodile looking guy, might have been able to swim across an ocean, but plants don't swim across the ocean. Okay, maybe birds carried the seeds in their poop. It could happen. I mean, that's what happens in like islands in the Pacific and stuff. But there are land animals too. This is a land animal. This is a land animal. And it certainly wouldn't be able to cross the Atlantic Ocean to get from South America to Africa or the other way around. So the evidence is that like these animals could not have migrated from one continent to the other unless these land masses were all one at one time. Questions about Pangaea? So all of this evidence, these are great exam questions because it's going to test your knowledge of like, how do we know? And it's more than just the fit of the continents, right? So it's all of this. It's the glaciers, the coal beds, the fossil evidence, the mountain chain, the mountain belt that we see. All of that is part of it. Okay. All right, let's start with divergent plate boundaries, and I'm going to see how far we can get here. See if we can get through divergent plate boundaries. Okay, so this map was painted by hand by Marie Tharp. This is her in 2001, I think. She was she was trained as a geologist and as an oceanographer, and she worked with a man, Heron, something like that. I don't remember his name. He went out on the boats and helped to collect the magnetic data that they needed and the sonar that was needed to see these ridges in the middle of the oceans. So ships would literally cross the oceans, dragging these instruments behind them in the water to measure. The sonar would bounce off of the ground and come back, and sort of that, the time it takes for the sound waves to go from the instrument to the bottom of the ocean and back, you can calculate how fast that goes, because you can calculate how fast sound moves in water, in salt water, and you can calculate how deep the water must be based on how long it took for the signal to come back. So that's the sort of thing that they used at first. And, you know, this was really, we really understood like after World War II, when we had submarines down in the oceans. So we knew that there were mountains down there. There are seamounts. There are, you know, that were volcanoes, part of old volcanic chains like Hawaii. And of course, these huge ridges that are pretty prominent when you're down on the seafloor. So it's not an old, flat, muddy bottom down there. There's a lot of evidence. So she painted this whole thing, and there was only one printer on the planet that could print something so large. But this was it. It's called the World Ocean Floor, and she did this in 1977. I was 5. So what I'm trying to say is, I don't think I'm ancient. This is new. This is new stuff. Geology. This is just try to make my point that geology is a new science. So we saw for the first time, there were 40,000 miles of these underwater ridges that encircled the Earth. And that is what led to the idea of seafloor spreading. And she was one of the first people to come up with this idea. The magnetic anomalies came later, and I'll show you a bit about that. This is a little bit more. So this is the idea of the sonar. Okay, so the boats had the instruments. This is showing from the bottom of the boat. I don't know where they put their instruments, but it would measure the depth like I described. So it bounced these waves off the seafloor. So it could see trenches. And this is what the sonar data looks like when it was plotted. So you could literally see the topography on the ocean floor. And that's how she put this all together. Here's the sonar data sitting on her table next to her painting. This is Marie Tharp again. And things, oh, these are cross sections of the ocean floors. These look like maybe the North Atlantic and the South Atlantic. I bet that's what that is. This is really cool. I mean, they knew to set up this photo, they knew that this was an important contribution to geology and to oceanography. This is just a tidbit that I found in reading about her. In 1952, as Marie Tharp was aligning 6, these are the 6, I think, sounding profiles that ran across the Atlantic, she noticed that all the profiles showed a V-shaped notch in the center of the ridge. This is not this kind of V-shaped notch. I don't think this is the V-shaped notch, is it? Yeah, maybe it is. Okay, so maybe this is the ridge coming up here, and then a V-shaped notch. We'll go with that. A V-shaped notch in the middle of those ridges. And she said the individual mountains didn't match up, but the cleft did, especially in the 3 northernmost profiles, Tharp explained. She thought the notch must be a rift valley, a place where the seafloor was spreading apart to make that V-shaped notch, with new material from below welling up around the fault and building the mid-ocean ridge. So she figured that out. But check this out. When I showed what I found to Bruce Heesen, that was her collaborator, the guy who went out on the boat, he groaned and said, "It can't be. It looks too much like it looks too much like continental drift," said Tharp. At the time, believing in the theory of continental drift was almost a form of scientific heresy, meaning the idea of continental drift, meaning there was before plate tectonics, just the idea that the continents had moved, it did not sit well with the scientists at that time because it was a new idea. And new ideas are often met with a lot of resistance. Trust me, trust me, it's true. Especially something as important as this. And it was a woman who found this. And this is what Hezen said. Apparently, almost everyone in the US thought continental drift was impossible. And Bruce initially dismissed her interpretation of the profiles as girl talk. Oh my God, how sexist. But it was 1950, what, 52? I'll just tell you, like, things haven't changed very much. I don't hear girl talk, but I hear things similar to it. Anyway, it still happens. But she stuck it out and she did awesome work. And I just wanted to point that out, that a lot of what you read in your texts and in the history of science are old white dudes. And it's not always the old white dudes that are coming up with all this. There were a lot of women backing up those old white dudes, their wives, their secretaries. They actually had secretaries at that time, helped them do their science, and they often didn't get credit. Okay, magnetic stripes. This is Vancouver. This is off our coast to the north. Here's Cape Mendocino. That's where the San Andreas goes offshore right here. This is California. Then this is Oregon. And then Washington State, Vancouver Island. So this is Canada. And these are what the magnetic stripes look like off. This is the Juan de Fuca Ridge is the name of the ridge that is between the Pacific plate and the Juan de Fuca plate, which is a small little bit of plate that's left over from the one that subducted here a long time ago, called the Farallon plate. There's a little piece left. And so just what I want you to see is the symmetry. So they've colored the different magnetic stripes. They're either positive or negative, meaning it's either normal with north pointing to our current north, or it's reversed, meaning it flipped. And so north was south, north became south. It happens because what generates our magnetic field? Do you remember? I'll just give you a second to think. It's the liquid outer core that's rotating and spinning along with Earth. And, you know, it's a liquid. It's probably messy. It's not a clean spin. And what happens is every once in a while across geologic time, the magnetic poles flip. And actually there's a guy down at UC Santa Cruz who works on this, and he says, you know, there's a wobble that's happening right now with the magnetic pole, and it could flip any day now. But still we have, you know, the north needle still points to the north today, so it hasn't flipped yet. Anyway, so that's what we're talking about, is literally over time, we have a record in the seafloor of the poles flipping. So we have normal that are colored and the reversed, which is white, or at least I'm assigning that. So the red colors are parallel across the ridge. The orange colors are symmetrical. So you see the same pattern on both sides. The green colors here, also symmetrical. So the width and the age of each of these, because we've dated these, we collect samples so that we know that the age of each of these magnetic reversals. That's what they're called. And so you can map it out. And even if you don't have a complete plate, if you just have a segment of information, a bit of information, you can match it up to this record that we've got now. And that tells us for sure, and this happened later, this was in the 60s that we collected the magnetic data. But that proved once and for all that yes, the crust was getting older the further you moved away from the mid-Atlantic rift. I know it's noon. I'm gonna keep going for a few more minutes because class doesn't technically end until 12:15. And I just like to get through a little bit more so that I have time on Thursday to talk about your lab and to finish this lecture. Okay, I will still stick around for questions afterwards. Here's a picture of a magnetometer being trailed behind a boat, and it's picking up a positive versus negative anomaly. And you know exactly where it was, so you can measure the distance, so how wide each of these anomalies is in the seafloor. And that's how we got this record of normal and reversed magnetic polarization across the oceans. Here's a little video that shows the upwelling of melt happening at the ridge, at the axis in this little V notch. And then we've got really young, buoyant, hot crust on either side. And so it forms a ridge on either side of this little notch. I'm going to play it a few times while I talk. So there's this little V notch that Marie Tharp saw on her profiles. Here's the ridge, one side of the ridge, the other side of the ridge. And then the seafloor sort of relaxes and sinks down to deeper depths as you move away from the ridge. So as the crust gets older, the oceanic crust gets older, it gets colder, older and colder. That might help you remember. And it becomes denser. And so the denser it is, the lower it sinks in the asthenosphere. So it sits down lower. So the highest point in the ocean floors are the ridges because it's hot, new, buoyant crust. So it's literally less dense because of the temperature of these rocks. And these stripes are the actual like normal, then reversed. The gray is normal, the white is reversed signal. And that signal is locked in after these rocks cool below the Curie point, which is a temperature in 500 and something degrees C. Once those rocks cool from a melt at 1200 degrees Celsius to somewhere around 500, I have to look up, 525 maybe is the Curie point, that locks in that magnetic polarity in those rocks, and you can't change it unless you heat them up again. Okay, so this is kind of like building the ocean. If you start off with creating some melts between North America and Europe, or South America and Africa, it starts by pushing those plates apart and creating a small sea. But over time, that sea opens up into an ocean. And I'll show you on the map some places where this is happening. And this is simply just showing you again in another way that you get these magnetic stripe reversals that are symmetrical across the ridge. So what kind of faults form in this? We haven't talked about faults yet, but they're the faults that happen when you get stretching, because you're pulling those rocks apart. You're moving the plates apart. So you're going to get something called a normal fault. We'll talk about normal faults next week. And you're going to get basalts because these are partial melts of the mantle, they're oceanic crust, it's all basalt. And this is the map. So you're going to use a map like this, but you're going to put it into Google Earth, and you'll be able to see exactly where in relation to the seafloor topography and the continents, where all this, the oldest crust is and the youngest. Everywhere you see the deep red, that's the youngest crust at 0 million years to maybe 10. And then it gets older. So the green crust is between, let's say 57 million years and 120 million years ago, or 127 million years ago. The blue and purple colors are 130 to 180. The scale stops there. The scale stops at 180 million years. Why? I'd like your input on this. I think I'm gonna have to stop at this one. I'll start showing you some pillow basalts on Thursday. We'll start up again here, but do you guys have any guesses? What would be?
It's because the old seafloor gets subductive and
Yep.
goes back into the mantle and becomes new, eventually coming back out again as new crust. So all the old crust, or it goes in back into the mantle.
Yep, it's part of those destructive plate boundaries, right? It gets sucked back into the mantle and remelted, basically, eventually. I see there was a question I missed. It said, what would be the effects of the poles flipping? I don't think that there would be any effects, except that our compass needle is going to point to the south instead of the north. I don't think it's going to have any other effects. Like, I don't think like animals are going to freak out, and I don't think we're going to start feeling funny or anything like that. I think it'll just happen. Because, I mean, we don't notice the magnetic poles, the magnetized earth very often in our day-to-day lives. All right, I'm going to stop here, you guys. The next thing I'm going to show you are these pillow basalts that are pretty cool. And I'll show you another video of what it looks like on the seafloor. We will pick back up on Thursday. But on Thursday, I am going to ask you to bring questions about your pre-lab, about Lab 5A. So please take a chance to try to download Google Earth and get it working on your computer. And try to get those 2 extra files opened in Google Earth. You got to open them with Google Earth. I'm not sure they'll work if you just double click on them. So go to Command O or Control O, find the file, or you can like right click on the file and open it in Google Earth itself. Okay, I'm gonna stick around for another 21 minutes, well, at least until 12:30. If anyone's got any more questions, feel free to stick around and ask.